Hello, my name is Zachary Chairez, and I'm a PhD student in the Department of Mathematics. A problem I've been working on is called the multi-view extension of the unbalanced Procrustes problem with an eigenvalue-based approach. So, what the original unbalanced Procrustes problem seeks to solve is we usually have a data matrix of high dimension, many observations, and many features. And what we want to do is represent this high dimensional data set as a smaller dimensional data set. And we want to do that with some kind of transformation, and we'll call that transformation X. So these kinds of problems can pop up in audio recording. We're trying to do some kind of voice recognition. We want to take a high fidelity image and we want to reduce that to a low fidelity image. Face recognition. We want to maybe learn how to predict a certain outcome given some kinds of observations. So this kind of problem is applicable in many kinds of fields. So what I propose to do is have a multi-view extension. And what this multi-view extension is, well, we still want to be able to take this high resolution data set, and we want to take it to a smaller version. But what happens if we have many kinds of data sets? C1, C2, C3, we can keep going to, 10 data sets, 20 data sets. We want to take all of these data sets to one common smaller data set. And we want to do this with their individual transformations, x1, x2, there should be x3. And what we want to do is, we want to make sure that they all go in the same area, or really we want them all to fall on top of each other. So our model here tries to do that. We want to minimize how close they get to y, but we also want to minimize how close they get to each other. And instead of solving this problem down here, which is the actual problem, we can solve this problem over here instead, which is an eigenvalue problem, which is much easier to solve. And one way to solve an eigenvalue problem is called a self-consistent field iteration scheme. So all this is going to do is, I'm going to make initial guesses at these x transformations. X1, X2, initial, all the way up to Xn. It doesn't matter how many data sets we can get. And I'm going to run it through this iteration where I'm just updating these x's every time. So update our x's until eventually we get where we consider, these are the best ones. So it's going to keep running through this iteration scheme until our output will be optimal values or optimal transformation matrices of x's. Okay, so what we did was we tested our algorithm on some preliminary data sets where we just randomized data sets. We randomized our small little matrix Y, and we randomized these data matrices C1, C2, and C3. And we tried finding their corresponding transformations that would take them there, X2, X1, and X3. And we randomized, so we assumed that each one had 3,000 observations and different numbers of features, and the size of y, because y is small, we wanted that to be of size 10. So what this iteration scheme tries to do is minimize that objective function every step. And based off of our graph here, that's exactly what it does. So we know at the very least our algorithm is working well. On top of that, we also want to make sure that our transformations get really, really close to each other, right? We want them to get very close to each other. So we all want them to be in the same ballpark. And we also, over time, take the average distances between each of the transformations, and it's about 10 to the negative 3, which is very, very small. So we know that our algorithm is working. We know that the transformations are right next to each other. The next step would be to take these to real-world data sets and try our algorithm on that, and then get some newer results. Thank you so much for listening.